Tuesday, 30 April 2023. Oh, excuse me, Tuesday, 30 May. Tuesday, 30 May 2023. Five twelfths. Last time, there's some reading of Solomon Lefschetz's selected papers, including the book he wrote, L'Analysis, which follows Poincaré's L'Analysis, or so, or perhaps it's as of after Poincaré's, and it was interesting that it implemented the intersection numbers in different notation, and he talks about Picard and Hodge, and most famous for the Hodge dual, and then also Bourbaki, but he separates the algebraic geometers, emphasis on the geometers, from the algebraic geometers, emphasis on the algebraic. And what does that mean? Well, when you look at something like the Banach-Tarski paradox, it's this idea of a doubling space. Well, what's a doubling space? It's after something that rises in topology, but that basically makes for whatever's in the scale on the order of 1, it ends up in the scale on the order of 2. And so the idea of the Banach-Tarski paradox is that a ball, the mathematical object, can be divided into 4 non-measurable pieces, or 5, depending on whether one of them is a point, at one of the poles, and these pieces can be reassembled, 2 or 3 in one and 2 in the other, into 2 balls of equal size. That they are as well still complete. That the emphasis on this doubling space is that what would otherwise be a matter of translation, because the only things that happens to these regions that are non-measurable, as is declared in the usual sense of the measure theory, that they're reassembled via translations and rotations, and results 2 identical copies. It doubles it. And really how this got started was for Vitali and Hausdorff. And they are geometers largely. And we're going to talk about Vitali as establishing the first kind of result that in the age of axiomatic set theory, because they're kind of along in the same age as axiomatic set theory, and the point set topology instead of the line of points, as it were. That the line is not really made of points in geometry; it's just an object. But in axiomatic set theory, it's that the point sets are an object, and so it's an object. So anyways, Vitali and Hausdorff then ended up providing what then Banach and Tarski extended their results and made this theorem, and it was called paradoxical because it makes a paradoxical decomposition of sorts. How can it be unmeasurable yet of a given analytical character yet arrive at twice so that's algebraic geometries. Then there's algebraic geometries, which takes in the different quite sense and tack the approach to a group and some other algebraic constructs about the contents of the point sets. It's not really geometric, it's algebraic now, the idea of derivation. So when you find a derivation of Banach-Tarski's paradox or theorem, if you can figure out a way that makes it so a doubling space is a real thing, and there are theorems about it because it's a topological action, that you'll often find that the derivation shown is algebras, not geometries. But really the origins are geometries, not algebras. Abstract algebra, of course, is a thing since algebra, or what it was 12 or 1300s or so, I forget when, for algorithms, for algorithmus, and algebra for algebra. The Muslims or the Arabic realm, when that was the center of the mathematical world, Arabic digits and such, that algebra then became group theory or abstract algebra or modern abstract algebra after Everest Galois or somebody like that, who then saw made for simple things like the integers, after Peano's integers, Giuseppe Peano's axioms for integers, which are successor, and then basically for the modular, establishing that addition and multiplication has that multiplication is modular after addition, modular, and which is modular after increment, in a sense. And as we discussed here, you can deconstruct arithmetic back down into addition and division. If you want a way to look at points as adding up to something and lines as dividing down to something, that's the way of things. So anyways, for group theory and algebra, after every Galois and groups, and then into Abel and the Abelian, and lots of stuff that goes on with Abel and the Abelian and Riemann and the Riemannian and the definitions of the integral calculus after Cauchy-Weierstrass. Because Cauchy and Weierstrass basically set out for the formal topology of the open topology, what results for it. But for delta epsilonics, that this is how we arrive at usual proofs for analysis, the fundamental theorems of calculus, with only a minimum number of extra axioms. Like least upper bound is actually an axiom to the complete order field, and measure 1.0 is actually an axiom to the complete order field. And thus the delta epsilonics stands it up and makes the square and makes quadrature and makes mensuration and makes integral calculus and the differential calculus, fundamental theorems of calculus after intermediate value theorem. That what you get into with algebra then is it frames it as models of objects, closed under operations, and with the existence of the finite fields and finite groups and the ZP and these finite modular groups and Z, when it's talked about the integers, it's like, let's have a group with all the positive and negative integers, which is fine, and it's fundamental. And then it's like, this suffices to be a model of our integers, and then we're going to build the rationals, and we'll call it the ordered field. It's a field. So you got a group, and then a field, and then the complete order field. This is the totally usual standard way that abstract analysis makes for formalism, that after courses in calculus already, which kind of grow from delta epsilonics, which don't really need much of this apparatus mostly. They're just built in the arithmetic that's the naive arithmetic already, with inequalities and trichotomy, that two numbers are either equal or less than or greater than each other, and that being less than is transitive, and being greater than is transitive, and being equals is transitive, Naive arithmetic. That then abstract algebra makes like the geometer's world less so first class or primary than the algebraicist's world. So there's two slightly different worldviews altogether. They're two fields of mathematics. They're different. Now, when Thomas Hardy, in his book Pure Mathematics, The Mathematician's Apology, he wrote about real numbers, and then he expresses first that their geometry is points, that the value that they have as magnitudes different from the origin. He expressed quite thoroughly that they modeled the same thing, and thus, in that sense, what you can make of from anything you can make of from algebra, geometry can too. And then, as to whether, well, geometry can draw a straight line if you can actually take an action of drawing these lines, and what algebra has for that is not really a thing. It would have to be kind of built all into it. So Banach-Tarski's theorem has these paradoxical decompositions or these paradoxical group actions, two different things that end up taking what's the measurable to the non-measurable and back to the measurable that happens to have exactly doubled it. Now, what this speaks to is Vitali's theorem about the existence of a doubling space. And so this was usually called the first thing, that's the existence of a non-measurable set. Because what Vitali did is he showed that if you took the unit interval, so this is like Banach-Tarski in 1D for a unit line segment instead of a three-dimensional ball of points. It's just a one-dimensional line segment. And so he splits that up into infinitely many pieces and shows that he can reassemble them to a line between length 1 and 3, say 2, for a doubling space. And so that gets into the notion of that in the time and in the space and in the milieu. Then what that made for the geometer is that the axiomatic set theorists couldn't really disprove it because he's a great geometer, Vitali. And so what they said was, well, this is where analytical character exits. So this is non-measurable, these sets. And then when he puts it together, they just say, well, that's just still non-measurable. Then as to why Banach and Tarski are kind of set up to say, well, each of these non-measurable spaces still kind of fills the outline of a sphere, and then it's density and extent and completeness and measure. Why that's called a paradox is one thing, but why that's called that he can reconstruct that after Vitali doesn't is what's kind of seems hypocritical. It is. It's not very critical. It doesn't really fulfill a critical comprehensive analysis. So when we look to revitalize measure theory, is to establish that this kind of doubling space is fundamental, and it can be built up after the non-standard for Vitali. And what it basically reflects is that if you have the rational numbers, and another definition of continuity, if you have the rational numbers for the signal continuity, if you could consider that a frequency and double that, then by an analog of the Shannon and Nyquist theorem and the continuum limit, it would be continuous. So the idea is similarly that that's kind of what Vitali does, then as to whether he separates those one-sided points on the line or two-sided points on the line, that when they're reassembled together and put back together, that they essentially go from being one-sided to two-sided. So it's kind of a combination of a couple things, and to make it in a non-standard framework with extended definitions of continuity and completeness, that it's an act that results in a doubling space. And so the idea is that when you draw points in a line for line continuity, they're kind of one-sided. Well, what side does the point have? Well, it has however many sides is what space it's in. It's kind of a half-dimensional space because it's only going up from 0 to 1. There's no real way to focus in on it, to tweezer it, to make a vanishing interval around it, to result at it as the result of computing 1/3 and finding it for the infinitely many digits that it needs to write its expansion to find its place in the line. It's one-sided. And so then the idea is in the field in one dimension that the points are two-sided, to the left and to the right. Then the idea is that for Vitali, when he starts with a line segment, and then he ends up splitting them all up, it ends up being all these individuated points of the continuum, that a continuum is made of an individuums. What are the individual elements of a continuum, the individua? That then it results for this doubling space is that basically it makes it so as if through definition only supported by line continuity, through a definition that will also have to be supported by field continuity, that makes it for a definition supported as by signal continuity, that it comes back together in a doubling space. So this is the kind of thing that makes mathematics better, because at the end of the day, there can be no paradoxes in mathematics. Anything that's left over as a paradox is just like, well, this is just a subfield, and these are its limits and bounds, or this is an error, or which is how it's usually described when a contradiction arises, that a paradox is, how can this be when these two things don't agree? That here it's described in terms of the dialectic in the middle of nowhere and the meeting in the middle of nowhere, and about how induction can't succeed. But then for somebody like Blaise Pascal's mathematical mind, for this intuitive mind, that it's an interesting play on the definitions and meanings of intuitive today and constructivist today. Because Pascal's intuitive mind basically follows inductive inference. Whereas today we would call that inference, oftentimes. That's the whole idea is delta epsilonics. It all leans one way. So you never have to rely on anything but an inductive proof. And so it's kind of the opposite today. What we would say would be like the formalist, say. Because then for a while, the formalist then made so that when the formalist ran into paradoxes, then it was called the intuitionists, the people who were left out of that. But for Pascal, these are his people with the mathematical mind. So Pascal was way before all this, and so we'll just leave it at that and get on with some more of Lefschetz here and talking about topology and results of Poincaré, intersections and the geometric. As Lefschetz is my new favorite algebraic geometer. Emile Picard and differentials on a surface. During the period 1882-1906, Picard developed almost single-handedly the foundations of this theory. Analysis with little topology. So under section 3, analysis of little topology. This is a rapid resume of the extensive contributions of Picard, Savari, and Poincaré, upon which I applied topology. See section 4. I will continue to consider the same surface F in all notations of 2. So got a topology of algebraic varieties. And then as with regards to that, a topology just defines density in neighborhoods. The open topology is the usual one of standard delta epsilonics. There are others. There are any number of others. There are some that are particularly sensible, fungible, and tractable. So he says, Emile Picard in Differentials in a Surface. During the period 1882-1906, Picard developed almost single-handedly the foundations of this theory. His evident purpose was to extend the Abel-Riemann theory, and this he accomplished in large measure. Reference Picard Simart, S-I-M-A-R-T. Picard studied particularly closed omega 1. That is, omega 1 equals alpha dx plus beta dy. D alpha over dy equals d beta over dx. So here, I'm going to refer back again to this identity dimension notion. So what's the identity dimension notion? It's like, well, we're only going to talk about numbers in the first quadrant and they're positive. May include 0, maybe not. May include infinity, maybe not. And so for the x, otherwise the x-axis and the y-axis, you can go ahead and just fill the whole page with that. You don't need to put it in the middle of the page. You can put it in any corner, fine. And then the identity is x equals y. So it's a diagonal line out of the origin, bisecting those axes and out to infinity, right? And so then the idea is almost sort of that, well, this x and y, you can think of them as one-sided, and then this identity dimension, you can kind of think of it as two-sided, but that's just an example of applying properties wherever they could go. It's like, well, this model only has 3 legs. Well, it needs to be painted with 3 colors. Well, then each one gets one, you know, that kind of thing. Or here, for example, well, the xy plane is going to have that some of these dimensions is going to be defined by line drawing, and so their points are one-sided. But then this function in them is two-sided somehow. Okay, it's the identity dimension. So then, reading this function here, it has like omega 1 equals alpha dx plus beta dy, and with this other constraint, d alpha over dy equals d beta over dx. It's kind of like d alpha over d beta equals dy over dx, which is 1 for the identity dimension. And so then any function that has that also would just be an offset line, because you can just add a constant or remove a constant from it. So these then being the, with the idea being things are symmetric about the identity axis, the identity dimension, these are just lines with slope 1 plus minus a constant. Picard studied particularly closed omega 1, that is this and that. Now, of course, it's much more general in the open upper half plane, or the plane of real numbers, or the Argand or Wessel complex plane. Here it's not, it's just simpler. And omega 2. The choice of closed W1 is very appropriate, since then the integral of the omega 1 is an element of K sub f. Kf. And K, as of after the 2 cycles of f, and the classes, K for the classes of f. I'm just flipping back a bit to see if I can find the definition of K briefly. Let f star be the non-singular predecessor of f in S to the n plus k, and let the u's to the n plus k be Cartesian coordinates for the s to the n plus k. And f star to the determined elements epsilon h less than equal to n plus k of kf. The system u sub h equals epsilon sub h less than equal to n plus k is a parametric representation of f star. F star is a model of kf. So the choice of closed omega 1 is very appropriate, since the integral of omega 1 is an element of kf, and analytic function theory plus topology are fairly readily available. So he's established that in this realm, in this milieu, for these things, for these differential functions, he's able to set up analytic function theory and topology. And so for function theory and topology together, then this is basically framed about there's Cartesian functions and this and that. And then analytic is either the analytic continuation of the functions, or otherwise the analytic region of the integral, or the analytic means several things, and it's been kind of sorted out what that means, because it's a pretty general concept, so it must have reasonably general application, but usually when it shows up, it means several different things in terms of the analysis overall. But an analytic basically means analyzable, or contributing to analytical character, or otherwise being analytical. And then topology is, as was noted. And then in a footnote he says, strictly speaking, the integral of omega 1 is in Kf only if omega 1 has no residues or periods. But since d omega 1 equals 0, yeah, it does. Well, see, because omega 1 equals alpha dx plus beta dy. So, that would be, if they're equal, because they'd be equal, that they're, that d alpha over d beta would be 1. That that a constant times dx plus a constant times dy is 0. So omega 1 is 0, and the integral omega 1. But since d omega 1 is 0, so omega 1 isn't necessarily 0, but the differential is. So that said, it's still kind of a so for at least some of the image of that model, some of the elements of it that satisfy at least these conditions. The integral of omega 1 is invariant under a continuous variation in the path of integration. Yeah, it is. It's invariant under a continuous variation in the path of integration. And that reflects for the much higher level things like the contour integral and such, or the path integral, about that it has the same kind of volume that it covers, or something like that. That otherwise, if it's not, is that if things depend on the path of integration, then that could get kind of contrived in as to whether when computing things like the area of a hyperbola rotated around the x-axis, which might have a value, but if you choose the wrong path of integration, it would appear to be infinite. These kinds of things. For closed one forms, the same three kinds as for abelian differentials are distinguished, save that for the third kind, logarithmic curves replace logarithmic points. Significant results are: 1. Closed one forms of the first kind make up a v to the q Castel Nuovo, q equals 1/2 r sub 1, as I have shown. 2. For the second kind, same property, save that they form a v to the 2q mod dkf. Picard. Regarding the third kind, Picard obtained this noteworthy result. There exists a least number, rho greater than or equal to 1, such that any set of rho plus 1 curves are logarithmic for some closed omega 1 having no other poles. Now, this is all quite above my experience at this point, because what I need to learn about are closed one forms, and the first, second, third kinds of these closed one forms, as about the abelian differentials, which abelian usually just means commutative in the algebraic group theory, but then the abelian is also ascribed to a couple different things, because Abel touched a lot of things in the early development of algebraic geometry. About logarithmic curves and logarithmic points. Now that these seem pretty clear, then with respect to like logarithmic points are probably kind of like integer points, except they reflect relations in the logarithmic, while the logarithmic curves are usually as of roots, or the inverse of the exponential, the logarithmic. Carrying on. Absent thus these definitions, reading the form, the two forms admit again three kinds. A, first kind, holomorphic, everywhere. B, second kind, holomorphic, to within a d omega 1 about each point. C, the rest. Holomorphic everywhere, holomorphic to within a d omega 1, which is 0. About each point in the topology. See the rest. The third kind is characterized by the possession of periods, residues over some 2-cycle gamma 2 bounding an arbitrarily small neighborhood of a 1 cycle on a curve. So then getting back to this notion of, well, what's a one-sided point and what's a two-sided point? It's like, well, I'm not quite sure what 1 cycles and 2 cycles are, and 1 forms and 2 forms, but I'll be looking to relate them in this kind of hierarchical manner, because then it will be able to carry across an operator calculus of them and make things simple for algebras. The 2 forms of the first kind were already found by Max Noether. They are of the type omega 2 equals q xyz dx dy over f prime of z, where q is an adjoint polynomial of degree n minus 4. These omega 2 or the associated q make up a VPQ, which is Castelnuovo, where PG is the geometric genus of f, studied at length by Italian geometers. So I have to go look into Castelnuovo and Picard a little bit, but these 1 forms, 2 forms, 1 cycles, 2 cycles, 1-sided, 2-sided, and this form of the closed form forms where the q equals 1/2 R1, with relating that to this some kind of a halving space. So in terms of doubling spaces, it's a lot more familiar to find things like a halving space, or establishing a triangle inequality, or working under root 2, and these kinds of things. Very usual. Let V P sub naught be the vector space of the omega 2 of the second kind mod D omega 1. The vector space mod D omega 1. So that's probably read as of that fineness, you know, or that it's modulo those quantities, however they're so vanishing. Picard utilizes topological description of finite 2 cycles to arrive at the following formula. P sub naught equals I plus 4Q minus rho plus 2. And then he gets into Savari and the theory of the base. The central idea here is a notion of algebraic dependence between curves on the surface F. I must first describe this concept. Let the non-singular surface F be in an S k plus 2. So this reminds of when we're talking about the harmonic functions, and the Laplacian is this second differential partial. And so when this sum of the second differential is partial, the differential taken twice, the partial in each dimension, and their sum is 0, then that's a harmonic function. And then how that works up is that in a lot of cases it only makes sense when n plus 2 has that n is greater than 0, so this rank or order is above 2. So then it goes up and comes down to 0 at the most. And otherwise, out of C empty functions, or functions that are infinitely differentiable, that they can be differentiated at least twice, and then when they have this property, then it kind of holds. So, and it's kind of similar when you think about the, and not necessarily related, it's just mathematical coincidence so far, of the Euler's graph formula and edges versus plus 2, or what, and when that's a way to win sprouts. Sprouts is a game where you start, you take turns drawing nodes on a piece of paper, and each term you draw a node. Oh no, you start by drawing any number of nodes, and the way to win is whether you go first or second, you draw an even or odd number of nodes, because there's a way to win if you know the order you play and the person you're playing picks wrong, essentially. The game of sprouts. So anyways, to play, then you connect two sprouts, and in the middle of that you add another node, and then when a sprout is connected to 3, it dies. And so and then you just keep connecting it, and the last person can move wins. So anyways, that's kind of like solving this with this Euler-Euler's formula, how to win at sprouts. But carrying on back to this mathematical coincidence is that this order of this term 2 in this function formula is as a matter of maybe the rank or order of the differential, what results, that then it's reduced and goes to 0. So let the non-singular surface F be in an SK plus 2. A linear system of hypersurfaces of the space cuts out on F a linear system of curves, C. A linear system of hypersurfaces of the space cuts out on F a linear system of curves, C. This system is complete if its curves are not curves of an amplified linear system. So that gets into the harmonics again as well. About then we need to follow up on what are definitions of, or rather I do, of amplified algebra, about this notion of algebraic dependence, because usually we'd be thinking about like linear independence, and thus that when you can arrive at linear independence, that it makes it possible to prove a lot of things about the existence of some system of equations. This algebraic dependence is something that establishes what's complete about it linearly or nonlinear. So Lefschetz says, we owe to the Italian school the following property. Every sufficiently ample, complete system C is part of a collection C of infinity Q such systems. The elements C of the collection are in an algebraic 1-1 correspondence with the points of an abelian variety V to Q, unique for F and called sometimes the Picard variety of F. A system C, infinity 2 at least, its degree, I suppose, without fixed points and with irreducible generic curve is said to be effective. Its curves are also called effective. So effective is, the usual meaning is effective means there's enough that it's basically without bound, like an effective infinity. So then the idea of this effective, I imagine would have a similar, it has a similar meaning. It's like it's actual, it's effective. It suffices to carry forward this rest of this completeness. And then he writes, note the following properties. A, an effective system is fully individualized by any one of its curves in this space. So he seems to be describing that it's fully individualized usually means that, like, it contains all its character, that it needs to reconstruct it. I'm not quite sure what that means. B, the generic curves of an effective system have the same genus, written bracket C. The curves CD of two effective systems intersect in a set of distinct points whose number is denoted by CD. Particularly, we write C squared for CC, and C squared is the degree of C. D, with CD as before, let two curves CD taken together be individuals of an effective system A. This system is unique, and we write A equals B plus C. So this writing of this, in this arithmetization of A equals B plus C, has that, it's kind of like the orbits and the trajectories where they're orthogonal to each other and how they add up and come together. And that this arithmetization, or A equals B plus C, is just representing, it's kind of like if they were to write the union of them, or otherwise that a set of them as a model of them. But he just says it's written this way, or we write. E says any two curves, A sub 1, A sub 2, an effective system, set A, may be joined in set A by a continuous system, infinity 1, of curves of A whose genus, except for those of A sub 1, A sub 2, is fixed and equal to A bracket. As an application of E, let ABC be effective and A equals B plus C, following Enriquez, connect A to B plus C as indicated. There follows a relation chi A plus bracket BC equals chi B plus chi C minus bracket BC. So chi A plus bracket BC equals chi B plus chi C minus bracket BC. And so we define phi A equals chi A plus bracket A squared equals 2 minus 2 bracket A plus bracket A squared. We verify once that phi A equals phi B plus C equals phi B plus phi C. That is, phi A is an additive function on effective systems. When 12.1 holds between effective systems, we set C equals A minus B. And we have phi C equals phi A minus B equals phi A minus phi B. So that's pretty great because it ends up making this kind of addition formula that phi A minus B equals phi A minus phi B. And then when you write it A equals B plus C is to be figured out when you want to write it as what is B minus C or A minus B, rather, that it can be written in terms of these kinds of identities arithmetically as an addition formula. Then in terms of what that has as an interpretation, says that this addition formula is only as that it affects a relation of sorts in terms of here. It doesn't say there's zero, it doesn't say there's anything else, it just has these formulas hold up. And he says, note also that as regards to the symbols, bracket BC, we may operate as with numbers, that is, and here he expresses kind of a distribution law, and there's associativity, commutativity, transitivity, and distribution. The bracket of this quantity B plus minus C, quantity times D, in the bracket equals bracket BD plus minus bracket CD. So usually when you see plus minus on one side and plus minus on this side, it's to be read that when it's one side is plus, the other side is plus, when the other side is minus, the other side is minus. Otherwise, there's another symbol called minus plus, which instead of plus minus having plus on top and minus on the bottom, it has minus on top and plus on the bottom. That reflects the opposite, that generally wherever you see plus minus, that it's, of course, respectively plus wherever it shows up, or minus. And whenever you see minus plus, it's the opposite. And then he goes on to define virtual systems. Let A, B be effective systems without imposing any further condition. Define a virtual system. C equals A minus B. It's a pair of symbols, phi A minus phi B. And then this bracket of the quantity A minus B squared. This defines automatically C, bracket C, and bracket C squared. It is also clear that they are the same for A minus B and A plus D minus quantity B plus D whatever D effective. In other words, C depends only upon the difference A minus B. Symbol C is called a virtual algebraic system of curves, and bracket C and bracket C squared are the related virtual genus and degree. Well, I'll have to study some more about this because while all these words are kind of familiar by themselves, only given this relation, what I still don't know about the one form is two forms, and the one cycle is two cycles, the one side is two sides. And these varieties to make up for this Picard variety, after the abelian and the Castelnuovo of the spaces that I've been learning about since today. It may very well happen that while A, B are effective, there exists curve C not necessarily effective, such that B plus C, B together with C, is a member of A. If so, C is considered as a curve of the virtual system C and has virtual characters bracket C and bracket C squared, not necessarily its actual characters. So that's interesting. It's calling out that there's these sort of void cases, or what would be singular in them, yet happen to actually just be kind of like falling out. That you can relate that to pretty simple things about like the singular, or like this identity dimension, which is in one sense a function in those two half dimensions, but when you continuously hinge that open so it's a half plane, then it's like three different dimensions besides. You can write the function in either one, and they have sort of translations between them. but it would be like 0. And so then it would be like for many differential systems, 0 is a trivial solution. It's like a root, and all the roots is 0, and the roots of this identity. Here it says a similar example in these virtual curves for these effective systems, in these virtual systems of these curves in the effective systems. If we define 0 equals a minus a as a virtual curve, 0 is unique. One readily finds that bracket 0 equals 1 and bracket 0 squared equals 0. To sum up, the totality of effective and virtual curves form a module, m sub s over the integers, the Savari module. So when we're talking about the modular, the regular, there's the regular, and then the modular is kind of ramified regular above it. Within m sub s, a relation gamma 1 c1 plus dot 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 gamma s cs equals 0 has a definite meaning. It is a relation of algebraic dependence between curves of f in the sense of Savari. So I'll be looking at the definition of linear independence with respect to that, the modularity and similar type things. The following remarkable result was proved by Savari, theorem of Savari. Well, I'm going to pick this up a little bit later. But that's where it's at there, theorem of Savari. We left off reading from Fourier analysis and Banach value problems. Now that we've kind of got an introduction to algebraic geometry from Lefschetz, we'll go back here to Gonzalez Velasco's great book on Fourier theory, and where we left on with the Fejer sums. So we just talked about the small angle approximation, the large angle approximation, the windows and the boxing that goes into the establishment of proofs of convergence of systems, a series of functions that happen to be orthogonal functions like sine and cosine in the Fourier analysis. About the Fourier style analysis with any of these two things, and about what goes into then making so for a kernel, like the Dirichlet kernel using the Fourier analysis, what makes it possible to establish that in the sense of the Riemann integration, or the Lebesgue, or whatever development and integration there arrives at, that it can be possible to make a Fourier style analysis up above that. For example, building one out of these effective and virtual curves of Lefschetz, as an example, without much further ado. These are these kinds of things that one gets into. So section 2.7 is Fejer sums, F-E-J-E-R, E acute, on the F-E-J-E-R sums. So far, the convergence of Fourier series has been found wanting on at least 2 counts. The Gibbs phenomenon is the most recent of these. This was the ringing and hysteresis that the overshoot then was defined by this. It's about 1.09 instead of 1.0 overshoot, and that's an invariant with respect to the amplitude and the height of the drop. In terms of sine and cosine and the small angle approximations, contribution to the Gibbs phenomenon. The Gibbs phenomenon is the most recent of these, but also remember that the Fourier series of a continuous function may diverge at infinitely many points. Both defects can be remedied using the following method to Fejer, 1880 to 1959. If we define S naught x equals 1/2 A naught, which is the first term of the Fourier series, and recall the well-known value of Snx for n greater than or equal to 1, the series, given by 4 on page 36, then we shall use the arithmetic means. The sigma n of x equals 1 over n plus 1, the mean of the sum from n equals 0 to n of Snx, of these partial sums instead of the partial sums themselves. Such arithmetic means had originally been introduced by George Frobenius in 1880 in his study of power series. So this very much reminds of the use of the means to get the convergence of the halving again and the doubling in the earlier development about the Dirichlet, if I recall correctly, where what ended up happening is that the 1/2 of the f of x from the left and x to the right is considered the value. So whenever there's a piecewise discontinuity that happens to be connected by a vertical asymptote in the analysis, then it's just it's the arithmetic mean of from the left and then from the right. So here, that the partial sums are averaged together to approximate the given function. Recall that by lemma 2.1 that the Fourier value of x equals 1 over 2 pi, integral from negative pi to pi, f of t, Dirichlet n of t minus x dt. For n greater than 1, where d sub n is the Dirichlet kernel, and observe this equation is also valid for n equals 0 if we define d naught equals 1 and recall the definition of a naught. So this gets into the why is there not b naught? Well, because it can be left out, and otherwise it kind of tips over. But maybe it should be there. It kind of is a thing. And what do we talk about what about 0? It's like, well, it's kind of in the middle, so it's special. And in fact, there's a definition about it, kind of hold it up in the middle. And going on, he says, then we obtain the following expression for the Fejer sum. Sigma nx equals 1 over n plus 1. The sum from n equals 0 to n of 1 over 2 pi, integral from negative pi to pi ft dn t minus x dt equals 1 over 2 pi, integral from negative pi to pi ft f of n t minus x dt. Where the f of n, instead of the Dirichlet kernel, there's this f of n, it's called the Fejer kernel. F of n equals 1 over n plus 1, the sum from n equals 0 to n of d sub n. We collect in a technical lemma the most useful properties of Fejer's kernel. The Fejer kernel has the following properties. Fejer n at t equals 1 over n plus 1. Sine squared times quantity 1/2 n plus 1 over times t, or sine squared 1/2 t greater than or equal to 0, if t not equal to 0 rather. And the integral from 0 to pi fn t equals pi. And for any number delta such that 0 is less than delta less than pi, the integral from delta to pi of fn goes to 0 as n goes to 0. Well, that's interesting, as it rather makes for that most of the contributions just kind of end up getting summed into the terms, and that what's left over has to be 0 because it's already kind of built into the contribution. It's interesting. All right. Well, that's a bit of a talk today, and what it's about is differential analysis, and even just looking at just a few lines of derivations, and basically how much scope, how much context, how much memory is required to keep the derivations, assumptions, and conventions sorted out, then that otherwise only the properties of the objects themselves end up being amenable to an arithmetization or algebraicization, so that then they can just be manipulable in any way by the means of arithmetic and algebra. And so with something like the algebraic varieties that Lefschetz talks about, this gets into pretty readily that his main tack is to get to a case where these definitions of these curves and their genuses and their ranks about their dimensions and about their relations, and for this particular differential equation for Picard's, gets to an arithmetization. Then for the Fourier analysis, it's also shown that for Fejer, worked to approach a way that something would find a bound or limit, or in this case an incongruity or a break. And so he worked out how to average that out over everything to get the idea of then that the natural tendency of that would be to square itself out, flatten itself out, and when so computed, it would just be kind of pulled in. And so then he makes for a form. And in this manner is an example that has to keep in mind a bunch of different things. Either one of those needs to keep a bunch of different things together. But the one sort of ends up funneling them into a tractable milieu, and the other one basically funnels them into a boot. Either one of which is tractable for various reasons. Then there's the idea that coming up with how those are considered as the derivations for their purposes is about how it's not really the language to relay that so much as to get the formulas. That when the derivation is done, then we're just going to use the formulas. That applying the formulas is much easier than deriving the formulas. But the goal is to be able to derive the formulas, generally. And to understand all these different ways to do it, because there's many possible ways to do it. There are various approaches. And some are more compatible with systems in themselves than others. Others are not. Some demand being the only case of the application of their kind of rule in the system, else there would be hysteresis. Others basically identify as being necessarily some of these complementary terms that add back up together. These kinds of things. There's two ways to look at any kind of inversion in mathematics. So this is kind of the idea of getting into, for this descriptive differential dynamics, what would be a least kind of working tool set, a least grab bag of derivations that help make up for that, the most ways of building up spaces to arrive at a bunch of these different ways of forms and continuations and closures, and when they're sensible and fungible and tractable according to these derivations, then also sensible, fungible, and tractable in the applications. So then we call these derivations side, this is the pure mathematics making a proof of so, and the applications is crunch the numbers, but it's all pure and it's all applied. Yeah. Those are just other sides of the coin. And so that gets into, for this descriptive differential dynamics, that it's dynamics in the differential, kind of like going back to the beginning of this talk, the doubling space of Banach-Tarski, which really belongs to Vitali and Hausdorff, the originators of the ideas that went into making Banach-Tarski's doubling space theorem, not a paradox. And the notions of the one side and two side on the line, and these kinds of continuity, and then how these kind of continuity make up for so that the decompositions and the group actions are put together in these ways that then make for something as simple as making for that down to a notation like an arithmetization of a formula for one forms and two forms, and one loops and two loops, and one cycles and two cycles. These various notions of these complementary duals that also kind of just reflect kinds or types. These are the things. Well, all right then, good afternoon.